Hello, everybody. I want to welcome you back from the first coffee break today to the second session of this day on snow and ice. I want also to remind you to post the questions on the Slido, and also please put the name of the presenter there that we know to whom the question is attended. This morning we will have 5 very interesting talks. And we immediately start with the first presentation. It is on coherence tracking and its adaptation to topsoil acquisition mode, a study case of Antarctic ice shelves. And this talk is given by Quentin Claude. Please, Quentin.
Oh, sorry, I was muted. Hi, everyone, and welcome to this presentation. I'm Quentin Claude. I'm a PhD student under the supervision of Franck Patain from the Université Libre de Bruxelles and Christian Barbier from the Liège Space Center. Today, I wanted to discuss a bit about the coherence tracking technique and its adaptation to the topsoil acquisition mode, but also some results over Antarctic ice shelves. And the flow line of the presentation will be to remind you why we are studying ice shelf, but also the result related to the technique we developed, and then how we can use this result in order to improve the quality of our interprograms. And so, as you know, the Antarctica is a large mass of ice which is set on a rocky continent, and this mass of ice is spreading into the ocean where it begins to float. And these ice shelves, the floating extension of the Antarctic ice sheet, are everything but passive in the sense that they have the ability to restrain the ice flow from behind by buttressing effect, but also laterally constrained by abatement and so on. And so if you remove this ice shelf, you can observe a huge acceleration of the ice flow from inland ice. And so you have a sea level rise. And this is quite concerning in a society where you have half of the human population in coastal areas. That's why we are studying ice shelf. And in that sense, we like to use SAR remote sensing because SAR remote sensing can be seen as giving a lot of tools that allows us to understand the geophysical parameter that governs the ice shelf's behavior. And in this presentation, I will focus on the 2D velocity shift. And the technique will be presented in Druning-Bundland in East Antarctica, where we have the Roboudon ice shelf with the ice flow coming from the Ragnin ice shelf with something like 300 meters per year velocity fields. One way to get the velocity field is to use SAR interferometry, already presented by several speakers. But the idea is to use the phase information from 2 acquisition dates and subtract the phase information in order to get an interferogram. And this interferogram is composed by different factors. And the one that we are interested in the displacement one by removing the other component of the interferograms. There's a theory, but in practice, what happens is that the ground scatterers are moving so fast over ice shelf that are moved up to several pixels away. And that's where coherence tracking comes from, because in reality, when you don't correct from this displacement and you do the phase difference pixel by pixel, you are measuring something where you have a total coherence loss. And so you have to take into account this displacement. That's where we are using coherence spectral tracking, where the goal is to find a IJ shift so that it maximizes the complex correlation between the master image and what given position, and the slave image at a shifted position around this X and Y position. And this is the goal of spectral tracking, where we try to maximize this correlation. And we are using the estimation of the coherence given by this formula. And this estimation of the coherence is equal to the coherence provided that we can respect ergodicity, which is already quite something ambitious when you are studying ice shelves and fast-moving areas. And in 2D, you can see it as a way to look for every position in the master image. You define a searching area, and then inside the searching area, we are computing for each possible translation a complex correlation that you put in a matrix, and then you find the best candidate which maximizes this complex correlation. In this example, we are studying an integer shift in this between the two images, but you can go finer by using supersampling technique. For example, in this example, you are using the curve Z supersampling technique. And in combination with this supersampling technique, you can also use 2D Gaussian fitting around the base candidate. So you take the best candidate, you take the neighbors, and then you have you can fit a 2D shift with the maximum representing the subpixel estimation of the bidimensional displacement. And when you do that for every possible position in the image, you have this kind of figures where you have for each pixel a rough estimation of the bidimensional displacement field, which already contains a lot of information, like this ice rises, for example, but also the ability of the ice shell to restrain the ice flow from behind, as you can see here, where you have an acceleration of this ice shell as soon as we go over all these ice rises and topographic elements. But on top of this bidimensional displacement field, you have also recovered the scatterers. So now we are able to correct the phase information of the interferogram. So in this study, we compare the interferometry currents using, let's say, classical interferometry, where you don't correct the displacement. And then we compute, let's say, what we call the tracked interferogram, where we compensate from the displacement. And in the classical one, we can see that as the velocity increase towards the Rocky glacier, you have a decrease in coherence around 0.4. And using tracked interferometry, you have a current around 0.81, which is quite good actually, especially if you compute the standard deviation of the displacement, which is linearly linearly dependent of the currents with this factor. If you take some sample of the corrected interferograms, you can see that using current tracking, you can really recover the interferometric information. Here we can see how we can now observe the boundary between the ice shelf and the ocean, but also in the below image, we have a totally recovery of the phase information, where in classical interferometry, you don't have anything. And on the top image, you have also a subglacial lake that you can observe just there, but nothing on the left image. And with this increase in fringe visibility, you have this increase in current. That's the goal of the technique. And that works for one example, but we wanted to see, to know what we can expect from current tracking. So we took 44 pairs of sine interferograms, from which we compute classical interferometry without compensation and what we call tracked interferometry. And so for each acquisition date, so this is date I, for example, where you have classical interferometry in blue and tracked interferometry in orange. And you can see, like the example I showed you before, the huge increase in current information. This is not systematic, as you can see in this acquisition, this pair, where between the two acquisition dates, you have a strong melt event. And so current tracking is not able to compensate for that. It allows you to go a bit finer in decreasing the temporal decorrelation. But in this type of events, you cannot do anything with current tracking. And what we can do is to look for each acquisition date, the current averages, and compute an histogram of these averages to have a good overview of the technique. And we splitted the result in fast-moving areas and slow-moving areas. And I will explain what I mean by that. And you can see that in fast-moving areas, you can expect to have strong increase in currents, even if it's not systematic, like in these melt events, for example. But you still can observe this huge current increase. On the right side, you have the slow-moving areas, and in these cases, you see that the gain in currents is much more questionable, meaning that in this type of areas, classical interferometry is more than enough. You don't have to compensate from the displacement. And by fast moving areas, I'm talking about areas moving at about 300 meters per year, acquired in by Sentinel-1 IW mode using temporal baseline of 12 days. And by slow moving areas, I'm talking about areas moving less than 100 meters per year. So that gives you an idea. One last element is that if you are using TOPSA acquisition mode, you have to pay attention that Sentinel-1 is acquired by a specific acquisition mode that induces an azimuthal phase bias. And this is clearly visible in the image. And one first element that you need to do using coherence tracking is to first deramp the images. Otherwise, when you are subtracting the phase information between the master image and the shifted slave image, you have a residual in the phase information from the slave image. And so you have this kind of residual that you can see a couple of times in the left image. So that's why you have to deramp the image before doing the coherence tracking technique. I think if I take a step back from the technique, it's rather simple. Considering a pair of co-register SAR images, in the case of a TOPSA acquisition mode, you have to first deramp the image before doing coherence tracking. And in the end, you have 4 products, which is the interferogram corrected from the displacement with the associated coherence, which allows you to get an estimation of the standard deviation of the displacement. But also as subproducts, you have a bidimensional displacement fields from the speckle coherent tracking. With that, I would like to thank you very much for your attention. If you have further questions, I would be very happy to answer you. Thank you.
Thank you, Quentin. Very nice presentation. So we have a few minutes, but that's okay. Let's go for the next talk that will be presented by Lynn Rouillet. And it's about mapping the timing of seasonal thaw subsidence maxima in central western Spitsbergen. So the floor is yours, Lynn.
Thank you very much. I hope you can hear me and see my slides now.
We hear you well.
Very nice. So my presentation is discussing the exploitation of INSAR for the detection of ground displacement related to a pretty different type of ice compared to the other presentation we had until now. It's an ice type that is not directly observable from space because it forms under the ground surface in cold climate environments, of course. But even if it's not possible to directly observe it from space, the effect of the ground ice on the surface can be documented because its formation and melting leads to ground level fluctuation. So our study takes place in Svalbard. It's an archipelago located between about 79 and 81 degrees of latitude north, directly up the mainland, Norway. In the glacier-free land of Svalbard, which looks pretty much like that, a combination of mountains and flat areas, part of the ground in depth is perennially frozen, which is called permafrost. But even in areas with permafrost, the upper part of the ground, which is called the active layer, is thawing during the summer and then refreezing in winter. And this part of the ground, the active layer, is typically 1 meter or a few meters in Svalbard environment. And this thawing and refreezing cause subsidence and heave due to the transition between water and ice into the ground. So it's a combination of a temporal effect and the phase transition of the water into the ground. This occurs on the whole landscape, But for this specific study, we will focus on flat areas where, for sure, the displacement is vertical. And in a former study, we process INSAR to retrieve seasonal displacement time series, and we compare this time series with active layer temperature measurements. So the active layer temperature measurement in boreholes in one region of Svalbard. So we have the whole information about the temperature until 2 meter depth, but also the surface temperature, of course. And what we could see is that the timing of the transition between the subsidence during the summer season and the heave when the ground is freezing back match really well the timing of the freeze back recording in the borehole. And not only this specific time is well represented by displacement information, but we can see also that small fluctuation of the displacement velocity or the displacement rate is also fitting fluctuation of the temperature. By example, this at the end of the summer, subsidence rate is decreasing, and it fits a period where the ground is start to cool down. So that study initiated a follow-up research to use seasonal INSAR displacement to indirectly document the thermal regime of the active layer at large scales, and not only at one specific location. And for this new study, we focus on 3 areas on the main Svalbard island, which is called Spitsbergen. Spitsbergen is affected by a pretty strong climatic gradient with higher temperature along the west coast, and also greater precipitation compared to the more continental interior. So in this study, we focused on 3 areas: Advandalen, Kaplinne, and Ny-Ålesund. And the objective is to document the distribution of and the timing of the cyclic seasonal displacement patterns, and then compare the time series with a model based on temperature measurements, and discuss the potential of using the timing of the subsidence maximum as a proxy of the active layer maximal thawing. So first, we processed INSAR based on Sentinel-1 in interferometric SWAT mode, acquired between June and November 2017 in a snow-free period. And we retrieved time series using a small baseline subset method SBAS. Then we applied several steps of filtering to focus on pixels with reliable and unambiguous cyclic patterns, and to focus on flat areas. And since we focus on flat areas, we could convert the line of sight displacement to vertical, assuming that there is no horizontal component on flat surfaces. And then we applied a really simple procedure, as the idea is to upscale and make it potentially easy to generate at large scale, and to extract the maximum of the time series and identify the timing of this maximum value, which is here called DOI, the day of the year, or which means basically the acquisition date of the maximum. And then we can finally map these products in 2 maps, which look this way. So on the top, you have a map showing the maximum subsidence for the considered period. And on the bottom, you see the time of this maximum value. And one thing we can already see if we select some areas in this relatively small area of some tens of kilometers long, is that we see spatial variations, and the timing of the cyclic displacement is actually gemomorphically controlled, within, in this case, earlier subsidence maxima in the fluvial sediments in the bottom of the valley compared to the valley sides composed of aeolian terraces. So this example here is for the bottom of the valley, while the top graph is on the side of the valley. Yes. And then we can here are the example for the two other regions. So with again the maps of the subsidence maximum value and the identify timing. And we could also apply an averaging for the whole area, so the entire region, to study the more of the general pattern of so subsidence and proceed. So this series here are now the regional averaging of the series for this area, and the vertical lines shows the interquartile range of the day of the year of this maximum. So one first thing we could do is then to compare basically the average for the region, or in that case, it's a median that has been plotted. And the first thing we can see is the subsidence maximum occurred later on the warm western coast, so in Kapliné and Ny-Ålesund, compared to the colder interior in Advandalen. We see also different kind of maximum subsidence values that are related to the sedimentology type and the sediment cover thickness and type. So in a way, this first finding fit the expectation that, of course, it's the transition between thawing and freezing is occurring later on the warm western coast, but it doesn't really confirm that the total variation of the displacement are indeed representative of the ground thermal regime. And that's what we of course want to analyze next. And for that, we compare the INSAR observation with a model based on temperature. This is a pretty simple model based on the Stefan equation. So the Stefan equation is a model that represents the progression of the thawing freezing front into the ground, based mostly only on accumulated degree days of thaw and freeze from temperature records. And this calculation then leads to the calculation of a composite index that is temporally variable, with increasing values in summer and decreasing values after the onset of the freezing period. And to compare this with INSAR, different scales, we normalize the index by its maximum value, and then rescale it by multiplying the values by the maximal INSAR displacement. And this gives some result like that. So on the left, you have the fit between the normalized index based on temperature, and not on the left, sorry, horizontally, x-axis, and the y axis is the observation, so the actual INSAR measurements. And this plot on the right shows the whole seasonal progression of the INSAR observation compared to the model. And in that case, it's a pretty ideal case. It's in Adondalen, so it's at a location, we compare this at the location of a borehole. Both the subsidence maximum, the timing of it, and also the wall progression of the displacement pattern is really well represented by the model based on the surface temperature. Now, if we look at the other example for the two other areas, so again, based on borehole temperatures, we could see that we found larger deviation at the pixel scale. So selecting just one pixel of INSAR information compared to the borehole temperature or the model, the composite index model. But when we average at either at a square kilometer or even regionally, it really improves the fits, which means that basically we get rid of unrepresentative local variations, and that allows for focusing on thermally controlled trends at a relatively large scale. So again, of course, there are still some deviation, but because the model is representing only a thermal variation, while INSAR is measuring all other processes occurring into the ground in relation with the ice formation. So, of course, one goal of the study was to discuss a bit the potential limitation of developing these kind of products at large scale. So and also comparing observation with model to learn about what are the controls of these subsidence and heave patterns. And we propose a quite straightforward model to extract those subsidence maximum and compare the S bus time series with a model, assuming that in a way, all the temporal patterns are mostly controlled by the temperature fluctuation. And obviously, we identify several limitations. For example, due to the late summer ground stabilization. Yeah, thank you. In where the ground level flatten, and then the identification of the day of the year is more noisy or more uncertain. This is one obvious limitation. Another limitation is that the model is not representing everything because it's based only on temperature, and you have different kind of complex hydrological effects occurring in the active layer. So this we will take this into account to improve the product in future research. But what we can already see is that the square kilometer averaging maybe favor in future product development to keep documenting the spatial variability, but also providing more robust phase statistics and more representative measurements. And also at this scale, one interesting thing is that the time series could also be easily compared and coupled with modeling of permafrost variable at similar resolution, by example, from the ESA Climate Change Initiative permafrost project. And yeah, so to sum up, our goal, or somehow the main relevance of it, is that in many applications, large-scale INSAR mapping strategy assume relatively constant displacement direction and apply an annual or multi-annual averaging to visualize the movement rate on a map. But of course, that doesn't work in permafrost environment because of these cyclic patterns. We need to develop dedicated products that can be useful for end users who want to study permafrost evolution. And the results of this study shows that with a relatively simple procedure, focusing only on the seasonal subsidence maximum and its timing, we can provide already some valuable products for the monitoring of polar regions. So that was it. Thank you for your attention, and you can contact me at this address if you want.
Okay, thank you, Linie. I just want to remind all of the participants in this session to put your questions into the Slido. And we immediately go on with the next presentation given by Jonas Andersen on improved ice velocity measurements with Sentinel-1 TOPS interferometry. Please, Jonas.
Hello, do you hear me?
Yes, but we can't see your screen.
Right, I still don't have the button. There it is. And... all right.
Okay, it works fine. Okay,
Perfect.
Jonas, please.
Okay, thank you. So hello, everyone. I'm presenting work here on ice velocity measurements with Sentinel-1 interferometry. And this is work that has been part of my PhD project and carried out with my colleagues and supervisors, John Merriman Boncori and Anders Kusk. Also, Christine Hvidberg, Aslak Grænsted, and Anne Solgaard have been involved in contributing to our validation. They should be acknowledged here as well. And finally, this work has also been contributing to an ESA project that we've collaborated with Inveo and Geos on. All right. So as we've seen in a few presentations here, sort of the current state of the art in general for ice velocity involves offset tracking, and it involves SAR due to its many advantages, and specifically Sentinel-1 has been used extensively due to its wide coverage provided by the TOPS mode in the IW acquisition mode. So to the right here, we see two examples of such offset tracking products. The first one is a multi-season map, so generated with data from multiple years. And then further to the right, we see offset tracking measurements made with only 24 days of data. So that is 2 cycles for each of the 2 satellites. And this somehow illustrates the need for averaging multiple cycles of data in order to sort of suppress the relatively high noise level in offset tracking measurements, specifically in the interior where the magnitude of the velocity is relatively low, so you get a very low signal to noise ratio. So conversely, differential interferometry or DINSAR in general, when applicable, gives very high accuracy and also higher resolution than can be obtained with offset tracking. One of the main downsides of DINSAR, of course, in terms of ice velocity, is that we cannot map the super fast-flowing outlet glaciers with DINSAR, as we completely lose coherence. So there we rely on offset tracking. But there's an obvious sort of benefit in using both of these techniques as they complement each other pretty well. However, with Sentinel-1, with the TOPS mode, it's not immediately straightforward to apply this in a scene with as much motion as there generally is over an ice sheet. And this is illustrated here by how the differential phase is now basically, we can split it up in 2 terms. And the first term is what we could call the zero Doppler line of sight motion term. So that's the phase term due to motion that we would expect also in a normal strip map acquisition. Another phase term, which is actually kind of here I've labeled it as the collective azimuth term, can be both caused by errors due to orbit errors and also effects caused by ionosphere, which has also been presented earlier in this conference. But a third term that is very relevant when measuring over such a highly moving scene is the term due to motion in the radar azimuth direction. And that term is generally not negligible in over these scenes. And so, yeah, so important to stress, of course, that this term, the motion term, is not exactly an error term as we would often label the other 2 terms. It's just a consequence of how the TOPS mode steers its antenna from aft to fore. But the consequence is that this term varies across the burst. So at burst boundaries, where we go from looking one way to the other, we can get these discontinuities in the phase, which can cause both just gradients in our resulting unwrapped velocity. But if the discontinuities are large enough, we actually might have trouble unwrapping across them, and we introduce unwrapping errors. So therefore, the rationale of this method is to actually eliminate this term due to azimuth motion. And in principle, this could be done by measuring azimuth motion within your given data pair, either with offset tracking or with split bandwidth techniques. However, based on our experiments, the better result proves to be using actually an external velocity estimate which is then projected to the azimuth direction and then corrected for in the image co-registration. And such an external map could, for instance, be the multi-year offset tracking map that I showed earlier, or it could be really any velocity mosaic that's then used, as you could say, the first guess of the velocity to correct this co-registration. Aside from that, there's an additional co-registration refinement, which I'll get to right after this slide. But then, aside from those two co-registration refinements, the processing chain, as you might notice here, is really the same as it would be for a strip map sensor. And this method is documented in this paper from last year. So, as I mentioned, the other co-registration refinement is based on spectral diversity. So, in the case of TOPS, there's two types of spectral diversity techniques that may be applied when we are searching for estimates of azimuth motion. And the first is the, I would say, well-known technique of bandpass filtering your SLCs and then forming a double difference interferogram which is then sensitive to azimuth motion across the entire image. And that can be done for sensor 1 as it can with any other sensor. The second technique that can be applied, however, is spectral diversity within the burst overlaps, where we already, without bandpass filtering, have measurements looking forward and measurements looking backward. So there, without bandpass filtering, we can simply form a double difference interferogram where we have sensitivity to azimuth motion and, in principle, also to any ionospheric effects that may be in the scene. So the plot here to the right shows the azimuth misregistration uncertainty translated into what would then be an uncertainty in the line of sight velocity, which is finally the measurement we are interested in. And here we can kind of see how the normal spectral diversity with the bandpass filtering requires these very large averaging windows of more than 700 meters in order to compete with the noise just in the normal interferogram. Conversely, the burst overlap technique, because of the higher sensitivity and the lower not requiring this bandpass filtering, allows us to not use very large averaging windows and still get noise that is lower than what is expected from the normal interferogram. So therefore, the second of these co-registration refinements uses this burst overlap technique to correct in the burst overlaps. And we'll see an example of how now. So this is an example where on the left, we show the sort of, you could say, naive approach of simply using a co-registration based on orbits and external DEM. And you clearly see all of these aligning with the burst boundaries, all of these discontinuities at pretty much every burst boundary. Instead, on the right is applied the refinement, the co-registration refinement based on an external velocity map. So this PROMISE offset tracking multi-year map we saw earlier. And here we see how most of the discontinuities are already well resolved just with this refinement, with the exception of a few. And in one of those bursts where we still see somewhat of a discontinuity, we show here, where on the left now we've only applied the external velocity refinement, and on the right we also apply this burst overlap technique. And here you see how the discontinuity, the original discontinuity, is well resolved. But of course, since we only have measurements in the burst overlaps, we now risk introducing two smaller discontinuities at either end of the burst overlap. And in order to suppress those, we apply an azimuth tapering function to these burst overlap azimuth shift measurements before applying them in the co-registration refinement. And so here, where now note that the azimuth is now horizontal here we have the original remaining burst overlap without the azimuth tapering burst overlap technique, and finally with the the tapering, sorry. And this technique is further documented in this paper from earlier this year. So finally, once you have your tensor measurements and your offset tracking measurements, those can be combined or fused in a weighted least squares problem. And in that problem, we assume surface parallel flow, as was also described, I think, by Jeremy earlier. And of course, if we want our measurements to be only based on tensor, which also Thomas described, we need these crossing orbits. We need both ascending and descending orbits, of course. Otherwise, we'll have to rely on azimuth offset tracking. And yeah, so this really also here on the right is just to remind that, of course, tensor is not a complete replacement for offset tracking, because again, we do have a lot of these areas, shear margins, and very fast moving parts where we will have to rely on offset tracking. Right, so here's an application example over the Swally 2.1 drainage basin, which is the drainage basin here that encapsulates the Northeast Greenland ice stream. And so here we've used 3 acquisition cycles from the previous winter campaign, and that consists of 4 descending and 3 ascending tracks. So in this area, we're also fortunate to have GPS measurements, a pretty extensive network of GPS measurements that is seen up here, provided by the eStrip team. And finally, as an external measure, we use this PROMISE multi-year map from 2016 to 2019, generated through PROMISE. Right, and here immediately is seen a result. So on the left is what we would obtain only applying offset tracking measurements, whereas on the right we have the combination of DINSAR and offset tracking measurements. And really, because this is a weighted least squares solution, because the accuracy or the noise in DINSAR is much lower, really all of the entire ice sheet, so the vast majority of this image consists effectively only of DINSAR measurements, because we do have crossing orbits here. And that's also immediately apparent. You can just from visual inspection, you can kind of notice how the noise level seems to be lower on the right side here. Also down here is shown the transect here, which passes by some of the GPS measurements shown as circles. And we can also see how the DINSAR measurements seem to align much better with the GPS measurements. And speaking of the GPS measurements, here's a more quantitative comparison. So here in red is highlighted the standard deviation between, for both the X and the Y component of the surface velocity for first the multi-year product, then the offset tracking campaign product, so the left plot before, and finally the right plot from before with the DINSAR measurements. And from here we can see that there's about a factor 5 improvement in accuracy with respect to offset tracking for the DINSAR product or the combined product, and even about a factor 2 improvement with respect to this multi-season product. So finally, the conclusion: the TOPS DINSAR approach allows a much improved exploitation of the very large, by now, Sentinel-1 data archive for velocity retrieval. Resolution and accuracy is greatly increased really wherever we can apply this, or wherever we have coverage and coherence in the interior. Another effect is that less averaging is required for this data compared to offset tracking. So this means that glaciologists who are interested in looking at sort of short-term changes in ice dynamics can now do so with this technique, of course, provided that there is actually coverage over their region of interest. So finally, the main takeaway, I think, from this project is that now the ice velocity measurements, the combination of offset tracking and DINSAR, is not really hindered by the TOPS mode, which seemed to be before the case. But now DINSAR and offset tracking can be combined, as it has been in the past, which we've also seen earlier. So yeah, that's it for my presentation. Thank you very much.
Thank you. Let's move to the next presentation. That would be given by Alexei Sharov, and it's about repeated surveys of the ice bridge in southern Spitsbergen from Sentinel-1 and ICESat-2 satellites. Please, Alexei, the floor is yours.
I'm trying to share my screen.
Okay. Maybe the button is not there yet.
No, I'm pressing the button. Okay, yeah, no, it is.
It works perfectly.
Mm-hmm. Good morning. 15 years ago, we carried out geodetic field surveys and mapped surface changes in an ice bridge in southern Spitsbergen using satellite ERS interferometry and ICESat altimetry data. And at the ESA FRINGE workshop in 2005, we reported on unusually rapid subsidence and local vertical movements in the central part of this ice bridge and predicted its collapse by 2020. Now is 2021, and the ice bridge is still intact, although it's getting narrow and thinner over time. And to explain the reason for our failed forecast, we decided to repeat remote sensing studies of this ice bridge. Just to remind, the most significant and massive ice bridges are formed by one or several tidewater glaciers stretching across water bodies and connecting isolated tracts of land to the mainland or larger island. And under current climate warming and essential ice loss due to Kelvin, surface ablation, and basal melting, ice bridges melt down much faster than inland glacier paths. And according to our estimates, there still exist nearly 30 large but still hypothetic ice bridges in the high Arctic archipelagos of Franz Josef Land, Novaya Zemlya, Severная Zemlya, and Svalbard. And the largest ice bridge, European ice bridge and known ice bridge, is situated in Hornsund in southern Spitsbergen at the northern latitude of approximately 77 degrees. This is a two-slope system of two divergent tidal glaciers, Hornbrain in the west and Hambergbrain in the east, both of surging type with a severely split surface and difficult access. And the history of surveys on the HH ice bridge is more than 120 years. And the hypothesis about the existence of subglacial strait was first proposed 45 years ago by Professor Vladislav Koryakin, my teacher. And subsequent surveys using radio echo sounding and ground penetrating radar in the area performed by Russian, British, Finnish, and Polish researchers, explorers, could neither verify nor disprove this hypothesis. And essential errors reached in the subglacial relief, in the subglacial bedrock heights reached up to tens of meters, and in some places where the positive relief of the glacier bedrock was shown, there is only seawater can be seen now. And generally, identifying of ice bridges, subglacial straits, and glacier-hidden islands and coasts is not trivial, and most of them will remain hypothetical objects until the end of their existence. And for the HH ice bridge, there is strong still evidence that its glacier bed is below sea level, which is due to the rapid subsidence of the surface at a rate of 1.5 meters a year or 4 centimeters a day. And the low and flat surface of the ice bridge with vague ice divide and without non-attacks and large depth of the seawater around the ice bridge also show or indicate that it's grounded on the sea bottom. And the bridge width reduced steadily from 25 kilometers in 1936 to 4 kilometers in April 2021. And the retreat rate for the ice bridge flanks was given 250 meters a year. The rapid atmospheric and oceanic warming with the inflow of warm waters in Hornsund are the most obvious reasons for the enhanced basal melting of this object and its shrinking. And the Hornsund climate recorded at the Polish weather station 30 kilometers westwards from the HH ice bridge became much milder and wetter. And in the last decade, the mean annual temperature increased from -5 to -2 degrees Celsius, while the amount of liquid precipitation has increased twice. Heavy rains in July and August destroyed the snow cover. And in summer 2020, there was very little snow on the HH surface, but many crevasses, as this high-resolution optical image shows. And the transverse orientation of crevasses here and here indicates the rather an extending character of ice flow in both parts of this ice bridge. New Sentinel SAR interferograms also show that the configuration of the ice bridge and the character of ice flow in this area changed drastically compared to the previous results. So in this work, we processed and used in total 19 SAR interferograms. We call them dual sense, so obtained from ascending and descending orbits with high coherency and obtained under steady and cold weather conditions in the period of 2019 and 2021. And the process of geocoding and geometric analysis of these interferograms was supported with the contemporary altimetric transects from the ISAT-2 satellite. And this set of standard interferometric products, including fringe amplitude and later coherence image, dated October 2020, represents the ice flow direction in the area and the composition of the ice bridge from of the main glaciers composing this bridge. So presently there are only 3 major glaciers which are actually contributing to the evolution of the ice bridge. These are Hornbrain Glacier in the west and Hamburg-Brain and Skjoldfjordene in the east. Okay, in the coherence image, you can clearly see the dark inflection line which indicates the potential position of the subglacial coast here in the region and enables its delineation more or less precisely. The next set of standard products dated February 2021 shows nearly the same position of the, shows nearly the same position of the inflection line here and here, here and here, and indicates an activation of the ice flow on the Skjoldfjordene glacier or ice cap. And it indicates also that the bedrock of the Hornbrain Glacier is below sea level for its entire length, for the entire length of this glacier. The next set, it's already, so I cannot see the D here, but okay, you can see it. It's a descending of it. I think it's a descending of it, yes. Data from October 2020, obtained from descending orbit, shows also nearly the same position of the inflection line. Okay, but more interesting, it shows also the presence of the fast sea ice in the Brepoling here in the west, which is, and the area of open water or Polinia in the Hamburg-Buchte here, and which may indicate the presence of the subglacial current here eastwards from the Brepoling, connecting Brepoling to the Hamburg-Buchte. So we suppose also that there is a continuous subglacial channel in the area. And the orientation of this channel, potential channel, coincides completely with the orientation of the Spitzbergen polar current and also with the route of the polar bears here in the area around the Sur Cap. So in this direction. Okay. And again, the coherence image from descending orbit shows the same orientation of the inflection line. And in addition, it shows the presence of some obstacle which hinders the ice flow to the Hamburg Buchte here within this narrow strip on the Hamburg Brain glacier surface. Then fringe images from 2019 and 2021, these are two, were used to measure frontal glacier velocities under the supposition that the glacier front speed is equal to the speed of the fast sea ice translation due to the glacier flow. And in the past years, the front glacier speed of Hamburg Brain increased from 23 centimeters a day to 29 centimeters a day, while the front speed of Hornbrain Glacier here decreased from 37 centimeters a day to almost zero. This might indicate that the Hornbrain Glacier is much thinner now. And in general, the triggering of an active to dormant phase in the ice flow is a very interesting effect to our understanding. It should be studied further. Okay, the next set of standard interferometric products demonstrates also the presence of the same hindrance or obstacle here, also here. And we suppose so this obstacle still underpinning the Hamburg Brain Glacier, and we guess that it might also support the longevity of this glacier and of the entire ice bridge. And this also hindrance can be seen as a small hill with a height of 14 meters in an optical image from April 2021. By the way, we used also such optical images for determining the heights of the glacier fronts, thank you, and controlled it also with the ISAT altimeter transects. So all elevation transects were geocoded for the corrected for the geoid height and overlaid on corresponding interferometric products. And in such composite products, each elevation spot within every altimetric transect receives corresponding phase and coherence values, which helped us to measure heights in the central part, precisely in the central part of the ice bridge, and changes in height at target points in comparison to the basic reference dam were determined, and the elevation change model has been generated, as it is shown here in this glacier elevation change map, in which the maximum height along the arcuate axis of the ice bridge was measured at 111 meters in 2019, compared to 130 meters in 2006, and the maximum change rate was given as 1.7 meters a year in the elevation, which is 3 times of the rate specified for South Svalbard, South Spitsbergen glaciers by Bamber et al. Okay, all points with low coherence and large decrease in elevation demonstrate or indicate the position and configuration of subglacial strait here. And we guess that the collapse of the ice bridge will lead to the emergence of a new Hornsunded strait here, which will separate the Torrell Land from Serkap Land and other islands. In a colder climate, the ice bridge will be rebuilt with sea ice flows that get stuck in the narrow Hornsunded. well protected from sunlight, and the triggering of an active to dormant phase in the ice flow of divergent tidal glaciers is an interesting phenomenon that requires further explanation, as I told. Thank you for the kind audience and sincere interest in this work.
Thank you, Alexei, for this presentation. I want to remind you to submit your questions in Slido, and we just go on with our next talk, which is given by Ludivine Libert on monitoring ice shelf track propagation using INSAR, examples of Brandt ice shelf of East Antarctica. Please, Ludivine.
Yeah, thank you. I'm sharing my screen. Do you see it?
Yes.
Perfect. So, as the title suggests, today I will tell you a bit more about the use of INSAR for monitoring ice shelf crack propagation. And this is a work together with my colleagues at NVO, and it's been done in the scope of the Polar Plus Ice Shelf ESA project. And to begin with, I think it's worth to agree with what we call actually a crack and explain why it's important, although it has been already bit explained in a presentation before by Quentin. So a crack is or a rift is a widely open fracture on an ice shelf, and as it propagates, it will threaten the structural integrity of the ice shelf, and it can lead to calving events, and the calving event will cause a loss of buttressing and an ice flow speedup, and overall an instability of the ice shelf. And unfortunately, so far, the mechanism leading to ice shelf breakup are still very poorly understood. Mostly because of the lack of observational data. And actually, there is quite some room there for improvement because nowadays we have really incredible data set with Sentinel-1 that is currently monitoring Antarctica margins almost completely. So most of the ice shelf are covered with at least 12 days and some even with 6 days. And this really offers a big opportunity to apply SAR interferometry or SAR imagery monitoring at large scale. And what is nowadays done mostly for monitoring crack propagation is the use of SAR backscatter image. You can compute time series of backscatter image as I show here for Larsen-C and Brandt ice shelf, and it shows you that the crack propagates a long time and leads to a calving event. But unfortunately, there is quite some limitation in the use of backscatter image, mostly due to the spatial resolution of the images, also the lack of contrast where the crack is very thin, and also due to the noise in the image. So might be interesting to go a bit more to the dynamical information of the ice shelf and use INSAR for monitoring cracks. And actually with INSAR, we can see the very, very small scale changes that are introduced by the propagation of the cracks. And by this definition, we know that an active crack has different flow velocity on both sides. So this causes a discontinuity in the interferogram. But we also can imagine that if the crack divides the ice shelf into regions, we can have also a different response to tidal bending. And as the crack propagates, we have also a stress field that is observed with SAR interferometry. And overall, actually, the crack appears in an interferogram as a discontinuity line between two phase ramps, between the two regions that it separates. And it's nicely shown in this interferogram of a Brandt ice shelf that shows the yellowing crack. And we see that indeed we have a discontinuity line that corresponds to the crack, and we can even see the stress field at the tip of the crack that looks like a raindrop pattern. And the fact that we see cracks in interferograms has been shown in quite a few studies already, but none has really propose a method for extracting this information and to exploit it at a larger scale for actual operational monitoring, for example. And that's really what we aim at doing in this work. We want to develop and propose a method for the automatic delineation of cracks with INSAR. And for demonstrating our method, I will focus on the rifting system of Brunt ice shelf in East Antarctica, so located here, shown by the red dot. And it's a nice ice shelf because it has quite a few well-known cracks, like Chasm 1 or Halloween crack that is more recent, and the overall rifting system is constrained at the McDonald ice ramble. That is basically the only pinning point of the ice shelf. And so it's really the point that control all the rifting activity on the ice shelf. And actually, there was recently on February 26, big calving event caused by the propagation of the North Rift. So this, well, here you see the North Rift before the calving event in September, and after the calving event, you have this big iceberg S74. And in the following, I will apply the method that will explain to track the timeline of the propagation of this crack. And so based on this, I generated the 6 days interferogram between between September 2020 and February 2021 over Brunt ice shelf in a given geometry. And this is an example of an interferogram with a close-up on the North Rift, so you can nicely see the discontinuity line here. And we can observe that on both sides we have indeed phase ramps with different fringe rate and orientation that are caused. We don't exactly know what is the cause, but that doesn't really matter for locating the crack. And we also see on this image that we have overlaid the calving front location after the calving event that has been manually delineated, and this is used for validation of the crack location because we don't have much data for validating this. And what we see is that in mid-November, we have a discontinuity line that is going up to this point, shown by the arrow. And if we go directly to the next interferogram, the discontinuity line goes to the next arrow, more or less, and still follows quite well the calving front line. And if we go at a later date, it still progresses quite consistently over time. So we have a discontinuity line that follows really the calving front and that grows over time. So it seems pretty consistent. But yeah, the problem is that we have fringes, and that's a complex information that's not so easy to manipulate to extract directly the discontinuity line. So what we do actually, since our assumption is that we have different fringe rate and orientation on both sides of the crack, we calculate the phase gradient because this is basically the translation of this information, right? So the phase gradient has a magnitude and an orientation. The magnitude relates to the fringe rate and the orientation relates to the fringe orientation, obviously. And you calculate it directly from the wrapped interferogram. So it avoids you to go through the phase unwrapping processing that is tedious and long and can introduce a lot of phase unwrapping errors. So that's pretty convenient. And you obtain this kind of images. So in the middle, you have the phase gradient magnitude, and on the right-hand side, you have the phase gradient orientation. And you see that in this image, you have indeed step edges in the image corresponding to the crack. So here you have the North Rift, here you have the Halloween crack, and here you have the Chasm. So you really see very well your rifting system. And once you have done that, you can simply apply an edge detection procedure on the image. But you don't want to deal with the angles because it's wrapped and it's not so easy to manipulate. So we just focus on the magnitude because you mostly have the same information in both. So we just apply edge detection on this image. That's really the key step of the processing. And what's the overall processing line? It's the following one. We just generate the interferograms, differential interferograms, calculate the phase gradient magnitude. We apply a Canny edge detection, so very classical edge detection procedure on the phase gradient magnitude. And for this purpose, we mask whatever is above the grounding line, because we know that the rifting activity is just limited to the ice shelf, and that the grounding zone is a zone where you can have a lot of crevasses, and they are also detected by the phase gradient magnitude edge detection. So we want to avoid that as much as we can. And in the end, the result of the detected edges are vectorized and cleaned from the small curvy lines to have a vector file of the cracks. And that's a kind of result that we can achieve here on the right. And we see that we can pretty well delineate the North Rift and also the chasm one. Unfortunately, it's more complicated for the Halloween crack, because this is a crack that is in part interrupted by snow bridges. So you have discontinuous detection, and somehow we need to be able to connect that. So that's one of the ongoing improvement. And we also have quite a few false detection here due to crevasses on the grounding zone. So the grounding zone is really on this area. And so this is ongoing improvement, but I'm pretty confident that we can achieve an even better result. And overall, I applied this method to our old dataset between September and February for delineating the North Rift. And I show you here a comparison between what's been delineated with interferometry on the right side, and at the same time, I show you the backscatter image acquired at the same time to have an idea of what's the sensitivity, the difference between both. And we start in September, and in September you see actually that the crack is already quite, well, it's quite advanced already, although it's quite stable also. And if you look at the Sorabacks, okay, and if you look at the backscatter image, well, if you have a big zoom and a very trained eye, you can see that it's going more or less up to here, shown by the red arrow. And on the next interferogram that I chose mid-November, we see that the crack didn't advance so much in interferometry, and the same in the backscatter image. And if we go directly to the next date, so second part of November, actually the crack starts to propagate quite quickly. And this can be also shown, seen in the backscatter image so far. And it consistently grows as we arrive in December. But at this point, actually, even though you detect with INSAR that the crack is still propagating and changing direction, actually in the backscatter image begins to be really, really complicated to detect. And we see that in January, we have almost all the extent of the North Rift that is delineated with INSAR. And January, it's 1 month before the iceberg calved, so it's quite sensitive actually. So of course, here you don't have anything delineated because the interferogram is incoherent. I mean, it's not the perfect method either, but it's very sensitive. And if you compare what's delineated with INSAR 1 month before, you have, in comparison, 4 days before in the backscatter image, you go up to there. So it's very much more sensitive than the backscatter image. And you can have with INSAR actually early signs of iceberg calving, which is really, really nice results. And so I go to my conclusion. I've shown you that SAR interferometry is a nice tool for mapping crack propagation, because it's very sensitive to small scale changes introduced by rifting activity. And with that, you can detect early signs of iceberg calving that are really useful for monitoring the ice shelves and plan what's the response also. And for modeling also, it's very useful to map the cracks. And this method combined together with the coverage, the acquisition plan of Sentinel-1 over Antarctic, since we have 6 and 12 the repeat over most of the margins, it offers really the opportunity to have a large scale systematic monitoring. Of course, the method has some limitation because you have misdetection caused by crevasses or artifacts, but and also you have decorrelation due to melt, snowdrift, and it's not applicable to fast flow, but it's foreseen that this will be overcome by the future Alpine mission like Roselle and NICER, and that's really a good opportunity for a synergy between sea and L-band sensor. And I will just finish by saying that this method has a lot of potential because it's so sensitive, and also you can with interferometry you can also obtain some actual dynamical information about the ice shelf response. That was my last slide, and thank you for attending and listening.
Thank you, Devin. So I think we're finished with the presentation, if I'm not mistaken. And now it's the phase where we can answer the questions that were asked by people that listen to the talks. So I don't know how we proceed. Maybe we go from the first speaker to the next, and each speaker can just read the questions that were on the chat and answer the questions. So.
Yes, so there was a question related to my presentation, and the person was asking why I'm not using speckle tracking, and maybe I was not clear in my presentation. Current tracking is one way to use current speckle tracking, but with the objective to recover the fast-moving coherence loss. And so instead of just looking at the 2D velocity field, we use this 2D velocity field in order to correct interferograms. And so to answer the question, I am using a speckle tracking technique with just a different objective. I hope it clarify a bit the talk. Thank you for the question.
Okay, then we go on with the questions for the next presentation. So this is on the mapping on the timing of seasonal thaw subsidence maxima in central western Spitsbergen. There were overall 3 questions. Line, can you just try to answer them?
Yes, thank you very much. So it was one question from Jeremy asking, you assume that displacement is only vertical. Is there any local lateral deformation? So yeah, in that case, we filter out all pixels in inclined terrain to focus on flat areas with a threshold of 1.5 degrees of slope angle. And so we can assume that it's mostly a vertical component. But of course, the integration of geometries is definitively valuable for slope processes. And this is something we have done in Svalbard for documenting direction of movement on downslope creeping landforms. Then for second question was from Alexei, right? Regarding the Stefan model, the Stefan equation. So there are different formulation of the Stefan equation. In that case, we used a relatively simple version, basically using only the accumulated degree days of thaw and freeze, and the coefficient representing ground properties assumed to be stable. So it doesn't take into account temporally variable hydrological effect into the ground. But I can share with you because the composite index has been used before and published in a geophysical research letter article from Yufan Hu. You can share this after. And then it was a question from Tazio about the scattering phase changes and possible bias. So this is not something that we have yet investigated into details. The reason is that, so we consider it in a way that we first applied a pretty conservative filtering of the pixel we selected at the end. So we filter out the most wet surfaces. And more importantly, the study focused only on the relative temporal variations. So even if the amplitude is partly biased because of the variation of the ground moisture, this should not affect much the directions of the movement and the transition from 2000 to HEAV. But that's that's something I'm really interested to look into more into detail in future research. And then it was the last one, right? From
Laurent.
Laurent, yeah. Can you explain a bit more? How do you compute the maximum of displacement time series? How you deal with noisy time series? Yeah, so I probably didn't explain that well. So it was really a simple procedure. I didn't fit any polynomial or look at the displacement gradient. I basically select the maximal value. And this was possible because we did apply this pretty conservative filtering and remove noisy time series by coherence, thresholding, aliasing thresholding, and also we only select for analyzing the timing, we only selected pixel with an amplitude over 1 centimeter, which means because we assume that if it's lower than 1 centimeter, the noise can take over and mask out the pattern, basically. But I guess, yeah, that's it. Yeah.
Okay.
Thank you, Lynn. I think the next speaker was Jonas Andersson about improvised velocity measurement with Sentinel-1 TARPS interferometry. And there was a few questions for you, so if you can please.
Yep. So first I see a question from Christoph Giesinger asking, how do you determine the weighting for the combining of offset tracking and INSAR results in the least square solution? So that's so for each velocity or deformation measurement from either offset tracking or INSAR, we estimate an uncertainty based on the standard deviation, or the variance it becomes then spatially in the image, and that is then combined for each measurement, and of course that will be generally much lower for the INSAR measurement. So where available, these will sort of dominate this weighted solution. And then there's a question from Rasha Miller asking, what is the temporal baseline of the dataset used for offset tracking, especially when fusing the two techniques, INSAR and offset tracking? So, so in order to make it basically the most fair for each method, so the best conditions for the INSAR measurements we found were using 6-day pairs, because then there's less motion, so we get to use INSAR further downstream of glaciers. Whereas for offset tracking, we found it was better to use the 12-day pairs, partially because of like a specific bias, you could say, between the A and B satellites that we experienced, which I think was also commented briefly yesterday by Christoph Giesinger. And perhaps I should also mention now that since we saw both from Thomas and Christoph this ETAT dataset for the offset tracking, we did not apply that dataset. So of course that would have maybe improved slightly the offset tracking measurements that we used. Yeah. And I think that's it. Unless I missed something.
I think that's okay. So we go on with the questions. There was one question on the talk from Alexei on repeated surveys of the ice bridge in southern Spitsbergen from Sentinel-1 and ISAT satellites. Alexei?
Yes, thank you for the question. This was, have you considered doing DINSA, differential interferometry, to see tidal motion and map more easily the grounding line? Yes, all our interferograms are differential. So we are doing practically classical and differential in SAR, of course. And we were trying to use tidal models provided, or tidal forecasts provided by the Oslo University earlier, but they provided actually for the Icefjorden, for Longyearbyen, which is nearly 200 kilometers away, and the character of tides in Hornsund is quite different. And instead of, and of course we used different reference elevation models. So basic elevation models derived from topographic maps, which were very inaccurate, and also present reference elevation models from the Tandem X mission, non-commercial, but which are also now already not inaccurate because changes are too rapid in the area. And instead, we tried to use ISAT-2 altimetry, concurrent altimetry data, and we estimated the tidal effects with this data. And for example, we detected that the sea level, or better to say sea ice level in Brepollen in Hornsund is slightly higher, half a meter higher than the sea level or the ice level in the Barents Sea or in the Hamburg-Buchte. Of course, and the last question about, sub-question about the grounding line. The water area, if any, open water area or channel is very narrow there. I have written it's less than 1 kilometer, and the sea ice thickness is still pretty high there. It's more than 150 meters or 180 meters, and the displacement, so and the slope is low. So I wouldn't speak here about the grounding line, but you're right, it's, what else? It's grounding line. Thank you. I hope I answered your question.
Yes, thank you. So the last speaker was Ludivine Libert about monitoring the ice shelf crack propagation using INSAR and an example on Brunt ice shelf in East Antarctica. I think you have one question that was from Alexei, is how did you calculate the phase gradients in practice?
Yeah, so in practice, the phase gradient is just a pixel by pixel phase difference, but in complex representation. And it's calculated over a small filter window. So that's basically how, and it's normalized by the number of the distance between the pixel, but actually you don't really need to normalize it by a distance. It's just a difference.
Thank you. I may have a last question, maybe for you. Is I wonder, we saw this presentation about machine learning at the beginning. Would it be something useful to map crack location using your phase gradient and phase direction maps that you have?
Yeah, I suppose can be. I haven't investigated yet because it's still early work. I mean, we are still investigating a bit on different ice shelf, what's the response in the interferograms. But I think in the end, yeah, probably also if you have misdetection to discriminate between misdetection and actual cracks, probably would be useful.
Okay, thank you. So we are exactly in time. So I want to thank all the presenters for this excellent quality of the presentations. I will also thank the technical team behind this to help us in a smooth transition between all the presentations. And I'm also want to remind you that this is not the end of Snow and Ice for Fringe. So we will have an excellent poster session this afternoon, starting at 2 to 3:30 p.m. So I hope to see you, everybody there at this meeting. And additionally, we will have a technical session on Snow and Ice at 4 p.m. this afternoon. And I want also to give the word now to Markus Engdahl to give some information on this. Markus, please. You have to unmute, please. Your sound is not working.
Hello?
Yeah, now it's good. Go on, Markus.
Yeah, sorry about the microphone trouble. Yeah, so I was saying that for the technical session, we would like to see a quick summary of the session, including the posters, but this is something just to set the stage. And then a set of seed questions or topics to start the discussion. So what are the pressing issues? What are the recommendations for the community, space agencies, etc.? And then just to remind you that then in the summary sessions on Friday, one of the chairs should present the full summary of what happened in this session.
Okay, thank you, Markus, for this. And I'm happy
Thanks
now.
to all of you.
Okay, thank you, Markus. I'm now closing the session. Thank you all for participating, and hope to see you all at 2 p.m. at the poster session on Snow and Ice. Thank you.
Thanks to everyone. Bye-bye.
Thank you, everyone. Have a
Goodbye.
nice
Thank you.
day.